So it's time to start the new lecture of Math F242. Good morning, students. I believe audio video is okay.
Yes, sir.
Great. So last time I have given you idea about the series and parallel system and how the reliability you can increase with the proper arrangement of the components. Then after the failure time distribution, Mttf, hazard rate function of the system of series or parallel nature we have derived. Then after we have started the question depending over that. So in series of that, we have the next question. A system has four identical components connected in parallel and shows a system reliability of 0.90. How many more components should be added in parallel to get system reliability of 0.99? So presently there are some components arranged in parallel gives the reliability of value 0.90. Now we want to increase the reliability up to the 0.99. So how much more components we require? So you know that for the reliability of the system in parallel, it is the 1 minus. If all components are identical, then it is the 1 minus RT of the component power n. So it is given to you that present reliability is 0.90, 1 minus RT power n. So from here, or instead of the power n, presently we have the four components. So power of 4. So this will give you the reliability of the component. So reliability of component is coming as a 0.4377. Now we want to increase the reliability as a 0.99. So here we have the 0.99, 1 minus. Now this reliability we have computed as a 0.4377. Now question is how much more components we require. So first we have to compute how many components we require. Then we can compute the increase in the number of components. So when the RS is 0.99 and components reliability is 0.4377 and they are arranged in parallel, so this will become 0.99 is equal to 1 minus 0.4377 power n. So here n will come 7.99. Since number of component it is, so we have to take the discrete value. So generally whenever we have the either the 7.01 or 7.99, in both case when we are talking about the reliability, so always we take the ceiling number. So here we have the 8. So when we have the 7.99, so because of the discrete number of components, so it will become the 8. Earlier we have the 4 components, now we require 8. So difference will become the 4. So 4 more components should be added in order to increase the reliability up to the 0.99. Right? Got? And this is very good question. Oh, this is not that. I will tell you. A certain type of engine seal is found to have life exponentially distributed with constant failure rate 0.03 into 10 to power minus 4. So here they have given the lifetime distribution as exponential distribution with lambda is equal to 0.03 into 10 to power minus 4. Now they are asking, if sometimes if we are giving that constant failure rate, then automatically it follow the exponential distribution, right? If there is no statement about the failure time distribution, only there we have the statement that failure failure rate is constant, so automatically you assume it is for the exponential distribution. What is the probability that given seal will last beyond the 1,000 hours? So you have to compute what is the probability that it will be functioning up to the 1,000 hours. So here it is given to you, the failure rate 1 upon b is the constant failure rate, so it is given to you as a 0.03 10 to power minus 4 failure per hour. So you know that reliability is what, if time to failure is follow the exponential distribution, then the reliability will be the e to power minus lambda into t, right? Either you say failure time, right? Because if failure time is given to you, no, rate is given to you, so it will become the e to power minus lambda t. So for the 10,000, okay, for 10,000, okay. So r at t is equal to 10,000, it will become e to power minus lambda into t. So it will become e to power minus 0.03. So by computation, its value will be the 0.97. So 97% seals will last beyond the 10,000 hours. So in this way, we can compute the required reliability. In the second part, we have to give the answer for what is the mttf for the of the seal. So you know, when time to failure follow the exponential distribution, then the mttf is what, 1 upon lambda, right? Either you can compute from 0 to infinity rt into dt, or for the exponentially distributed failure time distribution, then it is the 1 upon lambda, or you can say b, and b is given to you as a 1 upon 1 upon 0.03 into 10 to power minus 4. So it will give you 1 upon 0.03 into 10 to power minus 4, or 333 approximately hours. So this much is the mean time to failure of all seals, means average lifetime. It is the average lifetime. Now, part third, what is the reliability at mttf? So you know, when the when time to failure follow the exponential distribution, or we have the constant failure rate. So at that time, reliability at the mttf, right? You know the value. So it will become, so reliability at 333 will be the e to power minus lambda into t. So it will come 0.368. So last time also I have told you, approximately 37% components only cross the mean lifetime of a device. Only 37%, approximately only 37% cross or last beyond the average life. So it is very standard question for the competitive exam. If mean reliability at design life has to be at least 90%, what is the recommended design life? So if we want reliability should be 90%, then what is the design life? So you know that reliability is equal to e to power minus lambda t, and reliability we see zero point 0.9. So it will give you the design life, that is the t. So total t will come 35133. So that is, if our device is of 0.90 reliability, then its design life is approximately 35133 hours. Now this is important question from your book. Six type of components are available with prices and reliability as shown below. So we have the six different type of the components. So let us suppose component 1, 2, 3, 4, 5, 6 means these are the types, and their unit cost is given to you rupees 200, rupees 240, rupees 300, rupees 400, rupees 600, and rupees 1200. And reliability of type 1 component is only 0.2. Similar data for the component 2, 3, 4, 4, 5 are 0.25, 0.3, 0.5, 0.6 respectively. And for the last type 6, the reliability is given to you as a zero point 0.8. Here reliability is given to you zero point 0.8, and here we have the corresponding cost. Now question is, this is the given information. Question is, find the number of components and their type which should be set up in parallel configuration. Here we have to arrange these components in the parallel, so that, what is the condition, what is the objective? The reliability of the system is maximum. First we want the arrangement, parallel arrangement of from these components, so that reliability of a system is maximum and the total cost does not exceed rupees 1200. Means here we have the constraint of the money also. Then after we have one restriction also, all the total cost, all the components in the configuration should be of the same type. This is one more constraint. So total amount is given to you 1200. So in 1200 of type 1 component, how many components you can purchase? You can purchase the 6, because cost is 200. Unit price is 200. So in 1200 you can purchase 6 component of type 1. Similarly, if the unit price for the component 2 is given to you as a 240 rupees, 240, so you can purchase maximum 5. If unit price is given to you as a 300 for the type 3, so you can purchase only 4 components of same type. If unit price for the component 4 is given to you as a 400, so only 3 components you can purchase. And if the unit price of type 5 is 600, so only 2 components you can purchase. And for the sixth type, if unit price is 1200, so in 1200 you can purchase only 1. Now, so this is the under the constraint of maximum amount, this much is the number of components you can purchase for the different types component. Now number of components n, total cost per divided by the cost per unit, and reliability of n component if they are arranged in parallel, so it will become 1 minus rt to power n. That's, you have the enough knowledge for this. So if you talk about the this so number of components we have already discussed. So for the type 1 we can purchase maximum 6 item, 6, right. For the type 2 we can purchase 5. For the type 3, 4, 5, 6 we can purchase 4, 3, 2, 1 respectively. So the reliability of the system, if system contain the component of type 1, right. Reliability of the system if system contains the type 1 component, so it will become 1 minus r1 to power 6, because total 6 components we can purchase for the type 1, and its reliability is given to you only zero point 0.2. So 1 minus 0.2 to power 6. So reliability will come 7.34. Similarly, for the type 2, it is given to you component reliability is 0.25. So it will become 1 minus 0.25 to power 5. So it will become 0.763. 0.763. Similarly, the reliability for the type 3 component system, reliability of the system comprising with three comprising of type 3 component. So Rn will become, reliability of the system will become 1 minus 0.3 to power 4. So this value will come 7.60. Now the reliability of the system comprising with type 4 component, so it is equal to 1 minus 0.5 to power 3. So it will come 0.875. And reliability with component of type 5 will be the 1 minus zero point 0.6 to power 2, so 0.84. And for the type 6, because we have only the one component, so it will remain same, 0.8. So from here you can see the maximum reliability we can achieve, right. Maximum reliability we can achieve here. So we see that the reliability is maximum when we choose type 4 components, and number of component will become the 3. So here, under some restriction constraint, we are optimizing the number of components depending over the reliability to maximize the reliability. Now, this is a solved example of your book. I believe you can do that much. I have taught to you. So I believe now you can do this question. Let us have. Consider the system shown in figure. Next slide. The number inside the boxes are reliability, and number outside boxes are component numbers. Assume that components are mutually independent. You have the enough idea what is the independency means. The functioning of one component will not affect the functioning of the other. Find the reliability of the system. So here we have the arrangement of 9 components, and in box we have the value of the corresponding reliability, and outside the box we are nomenclating the component number ranging from 1 to 9. So I believe you can do this. So first, what is the arrangement of this subsystem? Then we have to see the arrangement of this system. Then we have to see the arrangement of this system. Then we have to see the arrangement of this system, right. Then we have to see the arrangement of this system, and then you can compute the reliability of the complete system. So reliability of the parallel subsystem S1 consisting of component 2, 3, 4. right? Here we have the 2, 3, 4. So you know that what is the reliability? 1 minus product of 1 minus reliability of the component. So it will become reliability of the subsystem S1, 1 minus 1 minus 0.75, 1 minus 0.80 into 1 minus 0.80. So it will come the 0.99. Then reliability of the series subsystem S2 consisting of the component 7 and 8. These 7 and 8 arranged in the series. So for the reliability of the series system, you know, it is the product of the reliability. So 0.95 into 0.95. So here it will be 0.9025. Then reliability of the parallel subsystem S3 consisting of S2 and component 9. So here we have this subsystem as a S3, this subsystem as a S1, this subsystem as a S2. So S3 consists the parallel system of S2 subsystem and component 9. So you know that 1 minus of reliability of the subsystem S2 into 1 minus reliability of the component 9. So this will come 0.99025. Means here what I'm saying, it is the 1 minus of 0.9025 into 1 minus zero point 0.9. Yeah, zero point 0.9. So this will give you 0.99025. Then after reliability of the series subsystem S4 consisting of the S3 and component 5, 6. So this is the subsystem S4. So it has, it is the series system having the component 5, 6 and subsystem S3. Subsystem S3. So reliability of the subsystem S4 will become 0.95 into 0.92 into 0.99025. So it will be 0.8654785. Then reliability of the series system S5 consisting of the S1 and component 1. So this is the subsystem 5. Right? Subsystem 5 having series system, a series arrangement containing the component 1 and subsystem S1. So reliability of subsystem S5 will become 0.99 into 0.98, so 0.9702. And for computing the complete system, we can see from that figure that S5 and S4 are in parallel. So reliability of the complete system will become 1 minus 0.9702 into into 1 minus 0.8654785. So reliability of complete system will become 0.9959912. So in this way, we can compute the reliability of the different type of the arrangement having the series and parallel arrangement. So that's all in the reliability from my side. Is there any problem? Anything you want to ask to clarify? So let us move to next chapter. So for a moment, I am stopping the recording so that I can start the next chapter with new link.